Okay, let's take up where we left off. Now, we talked about where we're fixing to head, so obviously we're fixing to get a little more complex. So we need to make sure we've remembered our formulas up to this point, have those written down so we can refer to them and keep going. So, talks about if two people push an object in the same direction, the total force equals the sum of two forces. So if two guys are on the same side of the fridge and they're both pushing in the same direction, with whatever strength they can, then if we add those two strengths, the result is going to be both of them added together. However, if one person's pushing one way and one person's pushing another, perpendicular, offset, then we're going to get a result that's a little different. We're not going to go either way, but somewhere in the middle of those two ways, as the photo illustrates here. And that's kind of what's happening electrically. The combined opposition to current flow from the resistor and inductor is called impedance. The unit of measurement is still ohms. So we're going to have to start calculating this impedance. And we still have to work with our inductors, we still have to work with our resistors, and then we have to kind of work with both of them together. So here's the new formula for ZT. Now we remember the 2 pi FL for inductive reactance. And now, if we want total circuit impedance when we throw resistors and inductors in the circuit together, it is ZT equals the square root of R total squared plus the X of L squared. So that's a new formula, and that is the impedance when we have both resistors and inductors within the same circuit. So in this circuit, ZT equals 50 ohms. So if we do that math, if we take the 30 ohm resistor, the 40 ohm inductor, the X of L figured out to be 40 ohms. We square 30, add it to 40 squared, and I'm talking about right here just in case anybody's not. So this 30 right here comes from right here. And this 40 right here comes from right there. So we're squaring both of those and adding them together. So if we square 30, we get 900. If we square 40, we get 1600. If we add those two together, we get 2500. We get the square root of that, we get 50 ohms, which is the overall impedance of this circuit. So we're going to have to see how that applies to another one. We're going to work some examples, I'm sure, so we'll go along. So now, if we want to calculate current, I total is equal to E over ZT. So once we calculate that overall impedance, we can get that overall current. So we're taking the 100 volts, and again, just to show you where these values are coming from, taking the 100 volts that's here. Remember, we calculated 50 ohms from the previous, because that was the 900 squared plus 1600 squared, give us a square root. We come up with 2 amps. So there's our answer right there before our very eyes. So that formula is much easier, as you can see. Once total current is determined, voltage drops are calculated. This is where it gets interesting, because we're used to the sum of these things summing up to be the applied voltage when we think about certain things. That's no longer the case. Those are out of the those rules are out of the game now. So we're going to actually do that in the next slide. So we're going to say 2 amps through 30 ohms gives us 60 volts. 2 amps through a 40 ohm impedance gives us 80 volts. Obviously, when we sum those, we get 140. So again, I told you those rules are out the door. So no longer applies. This is no longer true. So just forget that when we start talking about a mixture of inductance and resistance. But here's the new formula here, and it tells us that EA, voltage applied, is equal to the square root of ER squared plus EL squared. And we'd already calculated the 60 and 80 from the previous examples. So if we apply those to that, so I'm going to go back to the previous slide. Just remember, We went through here and we took the current and multiplied it times R1, the 2 amps. 2 times 30 gave us 60. 2 times 40 gave us 80. And we talked about how that could not be added together. So now we're taking those same values and we're squaring those, adding them together and getting the square root. That's how we get our applied. So again, new rules, new game. We've got to learn how to play it. So we're going to sum up these effects, and we're going to take this circuit here and we're going to start analyzing. Remember, this is going to be an involved process. We've got to take our time, step through it, and get them one by one. And that's what this example is going to show us. So here we go. Let's make it happen. The very first thing that we've got to do is calculate inductive reactance. So we can calculate the inductive reactance of each of those by applying 2 pi FL. And I'm going to do it on the calculator even though it's actually done right here for you. Now remember, K and milli will cancel each other out. So you got to make sure these units match up. So if we were just in henries and just in hertz, we'd be okay. But if one of these were millis and one of these were hertz, we'd have to be careful. But since milli is 10 to the negative third and K is 10 to the positive third, when we apply this formula, they cancel each other out. I'm going to use regular units. So that's 2 pi FL L1, which is 1.3 millihenries. So I'm going to say 2 times pi times, and I'm going to use the 1.3 millihenry. So that's 0.013 millihenries times 60,000, which is what 60k hertz equals. And we're going to come out, whoops, I missed a decimal point there, so let me try it again. It's easy to do when you're converting in your head. So let's write it out. Let's not convert in our head. We've got 1.3 millihenries, and this is where I went wrong. So we got 1.3 millihenries right here. So I'm going to add a few zeros in front of it. We've got to move this decimal 3 places. So I'm going to switch colors here so we can see that. So I've got to move it 1, 2, 3. So that's where I messed up. I had my decimal point in the wrong place. So let's go back and actually do this with the correct values now, and we'll come out with the same answer they did. So if I say 2 times pi times 0.0013 times 60,000 equals 490. I did it with just the millis and the k's, which cancel, and they got the same answer. So let's do the other one. We'll do it in units as well. It's 2.6, so it's going to be 2 times pi times 0.0026 times 60,000 equals 980. So we got the same answers, we just use units. I just wanted to make sure you understood that those two will cancel out, and if we go back to the base units, we don't have to worry about anything canceling out because we're using the formula as it should be. So we arrived at these two answers, the 490 and the 980, just as they did here. So now we've got to calculate XLT. So step 1 was getting the individual X of L's. Step 2 is getting total X of LT. Now we can just add those together, and that's what they did. We got 1470. So 490 plus 980 gives us 1470 ohms. So now we got to get our total. Now our total is going to be a little easier. We just add the 500 and the 700, and we get 1200. So much easier there to calculate. If there had only been one, our total would be that value. Now we've got to get ZT. And remember, ZT is this formula. So we got to make sure we're using it. ZT equals, it is the square root wow, it was a really funky looking square root of RT square plus XL squared. So we got our RT, we got our XLT, so we've got to apply that formula. So a couple of different ways to do it. If your calculator's got parentheses, this one does. So we're going to go 12, we're going to open parentheses, we're going to say 1200 squared, close parentheses, plus, and that was my RT, 14, whoops, I forgot to do a parenthesis, 1470, close parenthesis, squared. I think I messed up, so let me go back and do that again. So open parenthesis, 1200, close parenthesis, squared, plus open parenthesis, 1470, close parenthesis, squared, equals, and then we have to get the square root of that, 1897.6. I don't know if they're going to round or not. Let's see. They rounded all the way up to 1900, so that's fine. 1897, 1900, close enough. They came up with 1200, 1.44, 2.16. They got it. We're within 3. That's more than close enough. So we just didn't round. They did. And that's fine. All right. So IT, we've got to get that formula. So let's go ahead and clear out our formula here. Remember, IT was this. Whoops. That was when you got the drawing tool on. IT equals E over ZT. So let's plug that in. So we're going to take E, which is 120 volts, and we're going to divide it by divided by ZT, sorry, which is 1900. Now our answer is in ohms, so our answers will be in amps. So that is 0.063 amps, or if I move the decimal place 3 places, 1, 2, 3, I'm going to come up with 63.1, 63.2 milliamps. And they came up with 6.32 milliamps. I said 63, I meant 6.3. 1, 2, wait a minute now. I must have not times nodded right. Let's try it again. 120 divided by our ZT was 1900 equals 1, 2, 3. I'm coming up with 63. They wrote it wrong in one place and wrote it right in the other, so that's an error in NIDA. So let's circle that. This is the correct answer right here. So that was what's throwing me off. This is right. I absolutely agree with that all day long, but when they plugged it in over here, whoops, they messed up. So we've got a little error there that you need to be aware of. I'm going to write that slide down so we can hopefully get that fixed. So anyway, got to take note of that, but the right answer is 63.2, so we're good there. So let's see if we can finish up. We're running shy of time. ER1 is basically just a matter of taking that current and multiplying it by each one of these. Now I'm not going to take the time to do that, so there's just simply not enough time. But if we take this 63.2, not 6.32, remember this is an error. This right here should be 63.2. Multiply it by either the resistance or the impedance, we'll get the values of each of the voltage drops. So let's see what it came up with, and we'll take a look at this slide on the next